stopped and looked around, I mean, really looked, our world is constantly changing. You see it when bread bakes in the oven or when an apple slice starts to turn brown. And guess what? It's not magic, it's chemistry. And in this explainer, we're going to crack the code behind these everyday transformations.
Okay, here's a weird question for you. What on earth do sour milk, a rusty nail, and your own body digesting food all have in common? They seem totally unrelated, right? But there is this invisible, powerful process connecting all of them, changing them at a level we can't even see.
And the answer to that question, it's a chemical reaction. In every single one of those examples, the very identity of the stuff involved is changing. The milk isn't just warm milk anymore, it's something else. And once you know what to look for, you'll start seeing these incredible changes happening literally everywhere.
Just think about it for a second. Milk going sour, an old iron pan getting rusty, heck, even just cooking dinner tonight. What you're really doing is kicking off a bunch of chemical reactions. And get this, the very act of you breathing right now, that's a constant chemical reaction. This isn't just stuff for a lab. It's happening inside you and all around you, every single second.
So that's great and all, but how do we know for sure that a chemical reaction has happened? It's not like we can see the tiny little atoms rearranging themselves. But luckily for us, they leave behind some really obvious clues. You just have to know what you're looking for.
All right, here are the 4 big ones, the telltale signs. First, a change in state. Think of a liquid suddenly forming a solid. Second, a change in color, and I mean a real noticeable color swap. Third, the evolution of a gas, so any fizzing or bubbling is a huge clue. And finally, a change in temperature, either getting hotter or colder. If you spot one of these, chances are you're watching chemistry happen right before your eyes. You want to see these signs in action? Look no further than burning a magnesium ribbon. It is such a classic experiment for a reason. You get this absolutely dazzling white flame. That's a huge change in color and temperature. And then the solid metal ribbon turns into a totally different white powder. That's a change in state. It's the perfect example of the clues we were just talking about.
Okay, but describing that whole magnesium thing took a full sentence. Now, imagine you're a chemist, and you have to do that for every single reaction you study. It would be so slow and clunky, right? We needed a better way, a kind of universal shorthand to talk about these amazing transformations.
I mean, look at this. This sentence is totally accurate. It tells you everything you need to know. But writing this out over and over again for hundreds of different reactions? No way, it's just too much. Science needed something cleaner.
So step 1 was creating the word equation. Now this is a lot better. On the left side, you've got your starting ingredients. We call those the reactants. On the right, you have what you end up with, the product. And that arrow in the middle just means turns into. This is a huge improvement. It's so much more organized. But why stop there? We can make it even more efficient. We can take it one final step. By swapping the words for their chemical symbols, we get the chemical equation. And there it is. Mg plus O2 yields MgO. It's short, it's packed with information, and, this is the beautiful part, a chemist in any country on Earth can read it and know exactly what it means. It's the universal language of change.
Now that we have this new language, we have to learn its #1 rule. And this isn't just some rule a scientist made up. It's a fundamental law of the universe. It's called the law of conservation of mass. And what it basically says is, you can't just create or destroy atoms out of thin air.
And here's the crucial takeaway. Whatever atoms you start with, you have to end up with that exact same number of atoms. The count for each element has to be the same on both sides of that arrow. The equation must be balanced. It's like perfect cosmic bookkeeping. You can't cheat the system.
All right, let's actually try this. Here's an equation for iron rusting. Right now, it's unbalanced, see? We start with 1 iron atom on the left, but we end up with 3 on the right. That can't happen. So we fix it by adding numbers called coefficients in front of the molecules. It's like a little puzzle. You just go one element at a time. Let's start with oxygen, then hydrogen, then iron, and you keep tweaking the numbers until everything on the left perfectly matches everything on the right. And trust me, this isn't just for fun. Getting this balance right is absolutely critical for everything from making medicine to manufacturing steel.
And there we go, look at that. Let's do a final check. 3 iron atoms on the left, 3 on the right, 8 hydrogens on the left, 8 on the right, 4 oxygens on the left, 4 on the right. It is perfectly balanced. Our equation now reflects what actually happens in reality, and it follows that fundamental law of the universe.
So now that we have this language, we can actually start to spot patterns. It turns out most chemical reactions fall into just a few main categories based on how the atoms like to rearrange themselves. Let's check out a couple of the most common types.
First up, we have the combination reaction. And honestly, the name says it all. You take two or more separate things, your reactants, and they combine to form one single, more complex product. A plus B makes C. Simple as that.
A perfect example of this is making something called slaked lime. You take calcium oxide, add some water, and they combine to make one new thing, calcium hydroxide. And you know what else? This reaction gets really hot. Hey, sound familiar? That's a direct link back to one of our 4 telltale signs, a change in temperature. See how it all connects?
Now, on the complete flip side, you have the decomposition reaction. This is the exact opposite of what we just saw. Here, you start with one big complex thing, and it breaks down into 2 or more simpler products. So C breaks apart to make A and B.
A fantastic real-world example of this is heating up limestone. One single molecule of calcium carbonate breaks down into 2 simpler things, calcium oxide and carbon dioxide gas. And this isn't just a neat science experiment. This exact reaction is absolutely essential for making cement, the stuff we use to build our cities. It's a cornerstone of the modern world.
So, there you have it. We've gone from just noticing things changing to understanding the universal language that describes it all. You now have the tools to be a chemistry detective in your own life. The next time you see a car rusting, or bread rising, or even just take a breath, you'll know the code behind that change. So the only question left is, what reactions are you going to spot now?